Okay, I just wanted to make a quick video about the algebraic properties of matrix multiplication. Okay, in a previous video we went through and defined what matrix multiplication was. Okay, so if you haven't seen that video, go ahead and watch that one first. Let's go ahead and suppose that A, B, and C are matrices whose dimensions are such that each of the sums or differences and products are defined in the formulas below. Okay? All right, I actually haven't written any differences, but we'll talk about those a little bit later. Okay, let's look at these properties that we end up having here. Okay, so I'm assuming that all these make sense, okay? And if they do make sense, then we've actually got these equalities here. The associative property, do you remember the regular associative property of multiplication of real numbers? Okay, we have associativity when it comes to multiplying matrices, okay? So if I've got the quantity AB and I'm multiplying by C, okay, and all these products exist, then what I can do is just recombine these in a different way. That's A times the what? Product BC, if you'd rather do that. Okay, so we can move those parentheses around, okay? Now remember that we do not have commutativity, so you can't say AB is equal to BA, but you do have associativity, fortunately. Associativity is one of the most important properties to make an algebra beautiful and easy. If you don't have associativity, things get really nasty, okay? Commutativity is, or non-commutativity is something we can deal with fairly easily. We're used to the idea of one thing followed by another can be different than if we interchange them. If you're going to wash your clothes, you wash your clothes, then you dry them. That's not going to give you the same result as drying your clothes, then washing them, is it? Okay, let's go ahead and do distributivity. Remember that operation for what? Real numbers? Well, we've also got distributivity here when using matrix multiplication. A times the quantity B plus C. When I say the quantity, I really mean the matrix. Okay, you can actually what? Distribute the products this way. So that's AB plus AC. Okay, so if you didn't know any better, you would think A, B, and C are just real numbers, but they actually in this instance represent matrices. Okay, some people would call that the left distributive property because A is multiplying on the left, but you also have a right distributive property. So if I've got B plus C and I'm multiplying by some matrix A on the right, then this is also equal to BA plus CA. Again, assuming the dimensions are correct so we can actually perform all these operations. Okay, now I didn't mention differences here, but I will in this one. Okay, I'll actually write it down in red here. If this was a minus sign, is all I'm saying here, this would be a minus sign over there, and this 2 would still be equal. The same thing down here. So if this was a minus sign, this would be a minus sign down there, and those two would be still equal. Okay, so these could be sums or they could be differences. Okay. Now let's talk about something else called scalar commutativity. You got to have that word scalar on there because, again, we know matrix multiplication is not generally going to be commutative. If A is any scalar here, if I go A times cap A, so that's what a number times, or what we call a scalar, a number times a matrix, I'm going to consider that to be the same as if I take the matrix and multiply it by a number. Okay? All right. Scalar associativity. Okay? If I've got a scalar, again, A is any scalar, any real number or complex number, depending on the situation, little a times the product AB. You could do this. You could break this off and you could have little a times cap A and then take that result and multiply it on cap B there, that matrix. Or you could actually scooch this A all the way through here, and that is the same as cap A times the product AB. Okay, there's one other thing we could write. We could have AB times A on the other side if we wanted, using that property right up there, just above. But I eschewed that because that would actually be a theorem rather than well, I guess it would be okay. But that would actually come off of a little more work from these properties above. Anyway, okay. All right, let's take some concrete examples here. Here I threw in here, though, before we start here. Remember, I've said it multiple times now. Okay, AB and BA may be different. Okay, we do not have matrix commutativity when we multiply here. We do when we add, because you're just adding, right, entry by entry. But our last multiplication is kind of weird, and it's not commutative. Okay, sometimes these are equal, but sometimes they're not. Sometimes one exists and the other might not even, right, if the dimensions are wrong. Okay, but enough said on that. Let's get to concrete examples of these properties I've mentioned here. When it comes to the distributive property here, I'm just going to mention, or just give an example of one of them. I'll do the right distributive property here. Suppose cap A is 1, 2, 0, 3, cap B is negative 5, 4, 7, 2, reading across here, and C is negative 4, negative 3, 1, 9. Okay, I'm going to go A times the quantity B plus C here. So the first thing I'm going to do is add B and C in, well, that's not the first thing I'm going to do. The first thing I'm going to do is write down A. Okay, so 1, 2, 0, 3. But the next thing I'm going to do is put down the actual, as an operation, this is the first thing I'm going to do, is add B and C here. And remember, you can add these two because they have what? The same dimensions. So adding B and C, remember you just add corresponding entries. So I'd have negative 5 and negative 4, and that would give me the negative 9. 4 plus negative 3 gives me the 1, and so forth. Okay, so we've got negative 9, 1, 8, 11 when we do that. Okay, now when we perform the matrix multiplication, you remember you multiply what? Column by column. Okay, take the matrix that's on the right in the product, so that's the second matrix here. Okay, the negative 9, 1, 8, 11, and start from the leftmost column and start multiplying like we started to, right? Imagine it's transpose, multiply, and add corresponding components or corresponding products, okay? All right, what we get here, we would get negative 9 and 2 times 8 is 16, okay? Negative 9 and 16 is 7, okay? Do it down here, 0 times negative 9, 3 and 8 is 24, that adds up to 24, okay? And then do it with this column. So the 1, remember with the, let's maybe write it here just to help you guys. 1 and 11. Multiply 1 times the 1 and add to that the 2 times the 11. And you would get what? 22 and 1 is 23. Okay? And then do it with the second row. 1 times 0 is 0. 3 times 11 is 33. Adding those, we get 33. So there's our answer. Okay, another 2 by 2 matrix. Okay? And now let's look at it this way. Let's try this and see what we've got here. I'm going to go AB plus AC. Okay, so there I've written down the matrices that I've got. Okay, so you might stop and do this yourself as we go along and see if you don't get the right answer. Okay, so I've got AB 1, 2, 0, 3 times negative 5, 4, 7, 2. And to that I'm adding A times C, so that's 1, 2, 0, 3, negative 4, negative 3, 1, 9. Okay, let's take the products here. Okay, so I'd have negative 5 and 14 is 9. I'd have 0 and 21 is 21. Okay, got those two. Let's multiply with the 4, 2. So that'd be 1 times 4 is 4 plus 2 times 2. That would give us 8. And I have 4 times 0 plus 3 times 2 is 6. Okay, so there's my product there. Let's look on this one. Okay, so I've got negative 4, 1, multiplying on 1, 2, 0, 3. So let's go like this. 4 times negative 1, or 1 times negative 4, I should say, is negative 4 plus 2 times 1. That will give negative 2. Okay, negative 4 times 0 is 0. To that I'm adding 3 times 1, so that will give me the 3. So I've got these two. Okay, let's go with the negative 3, 9 column here. Negative 3 times 1 is negative 3. 2 and 9 is 18. Those add to 15. Negative 3 times 0, 3 times 9 is 27. Adds to 27. Got it. Now let's add those two matrices. Okay, just add corresponding components. Very simple because you're just adding. 9 and negative 2 gives you 7. 21 plus 3 gives you 24. 8 plus 15 gives you 23. 6 plus 27 gives you 33. And what do you notice? Lo and behold, these two are equal. Okay? Just like I claimed they were. Okay? So what I did was give you a concrete example of that first distributive property that we have up there. Okay? This guy. Okay, I'm not going to give you an associative one, but we could do that, I guess. Okay, instead I chose this distributive law here. Let's go 3 times AB. Okay, not this distributive law, this scalar associativity law. 3 times AB, we already computed AB, it was right above. So I can go 3 times 9, 8, 21, 6. That'd be 20. Remember, with scalar multiplication, that 3 is going to multiply on every entry, so that'll be what? 27, 24, 63, 18. Okay? And instead, let's go 3a first and then multiply by b. So 3a would actually be what? 3609. And then I'm going to multiply that by b. b was negative 5472. Let's go ahead and multiply those. That'd be 15 and 6 times 7 is 42. So 42 minus 15 is 27. Yep. Okay. 0, right? 7 times 9 is 63 when we add those. Okay, check. Let's go with a 4 and 2. That would be 12 plus 12 is 24. Okay, good. 4 times 0 is 0. 2 times 9, that will give us 18. Check. These are equal. Okay, just for the very last one here, I'm going to scooch that 3 over to the b here. I'm going to go a times 3b. So there's my a, 1, 2, 0, 3. My 3b would be what? Negative 15, 12, 21, 6. Let's try it again. Okay, last one here. 15 times 1 plus 2 times 21. That's 42 minus 15, really. 27. Looks familiar. 15 times 0 is 0. 3 times 21 is 63. Check. 12 times 1 plus 2 times 6 is 24. Check. 12 times 0 plus 3 times 6 is 18. Check. They're all the same. Okay? Alrighty. I guess I didn't do the very first one, the associative one. Okay? Why? I'll leave that as what? An EFY. The EFY is not matrices. What is EFY? That's exercise for you. Okay? So you might try this and do it these two different ways and see if you get the same answer. Go ahead and use this A, B, and C that I've got here and see if it doesn't work. I promise you it will. But it's good to actually see it working once in a while. Okay, one last thing I want to drop in here. Again, this is just a short video. Transposes in matrix multiplication or transposition. Okay, do you remember what the transpose of a matrix is? You just what? Turn every row into a column, or if you want every column into a row, right? Okay, it amounts to the same thing in the end. Okay, if A and B are matrices such that AB exists, okay, so the dimensions are right, so AB exists, then if I take AB and take its transpose, okay, I get exactly the same thing as if I go B transpose times A transpose. Okay, notice something funny has happened? What the order of the product has turned around, right? In the inside of the parentheses, A comes first, but once on the outside here, I've got what? B coming second, but with these transposes on both of them. Let's take a concrete example. I'm not really going to prove this, but let's go ahead and take another concrete example. I'm going to use the A and the B that we did in the previous examples. Okay, so A is 1203 and B is negative 5472 reading across. Okay, we already computed this before. AB is 98216. Okay, so the first row becomes the first column. So I've got what? 98 written up and down, and then 216, that's going to be my second column. So that's the transpose of the matrix AB. Notice the need for parentheses here, because if I just wrote AB and then just put my transpose symbol like that, what does that look like? It looks like I'm going A times B transpose. Do you see? It looks like you'd be going like that. A times B transpose. That's not what we're doing. I'm going A times B and then taking the transpose of the result. Okay? So I hope you see why we need the parentheses there. Anyways, moving on. Let's go ahead. I'm testing this thing up here, right? So I'm going to go B transpose first. What's B transpose? So negative 5, 7, which is a column here, becomes a row instead. Let's think of it this way. And then the second column becomes what? The second row. Okay, so I'm thinking of this in different ways. Okay, the rows turns into columns. Columns turn into rows, whichever way you want to think about it here. Okay, A transpose. So 1, 2, that row becomes 1, 2, what? The first column. The second row, 0, 3, becomes what? The second column, 0, 3, written up and down. Okay, now let's go ahead and multiply these two fellas. So I've got B transpose times A transpose. It'd be negative 5, 7, 4, 2, reading across. 1, 0, 2, 3, reading across on A transpose there. Let's take their product. Okay, let's multiply that by the 1, 2. So we'd have 1 multiplying on the 5 and the 2 multiplying on the 7. That'd be negative 5 plus 14. That'd be 9. Okay. And then I'd have 1 times 2, 4 is 4. 2 and 2 is 4, so that would give me the 8. And 0, 3, the 0 would multiply on the negative 5, and the 3 on the 7, that would give us 21. 0 multiplies on the 4, 2 times 3 is 6. Okay, what do you notice about these two things? They are equal. Okay, well, I hope you understood that. I don't know how much use we're actually going to have for this, but I thought it would be nice to throw that in there, showing it. We're going to have something like that happen with inverses also, though I have not discussed inverses quite yet. Okay, all right.